Good afternoon, or Tuesday, April 4th, 2023, as it were, or as it were. uh, a sunny day, partly cloudy. Today I thought I'd talk some more about the path integral. And the path integral is in the sense of, as we've been talking about the nonlinear contributions and the harmonic theory and the theory of potentials, that the idea of the path integral is that it's like the line integral. And this is where the line integral is how to measure the length of a line or a curve. Is that a function defines a curve, and thus that the length of the line or curve as is in accordance to following this and essentially rolling a measure as over it that according to the number of revolutions so arrived at by the outer circumference of this measuring wheel, that the tracing the course of this line works out that by walking the line you can measure the length of the line. And so there are various approaches to try to measure the length of the line, because when you introduce a curve, and here we're talking only about smooth curves and not kinks or right angles of any sort, but the orthogonal, but only specifically of smooth curves and lines, that when measuring the length of the line, there's an approach for a straight line that is very clear cut, that the length of the line is in accordance to its parametric form as a line and the two endpoints of the beginning and end of the measurement. But measuring the length of a curve is somewhat and quite more difficult. And when it's introduced in the curriculum, a line integral, there are various approaches to making the line integral. And some of them depend on essentially the quadrature and diminishing squares and this kind of thing, where the idea is that by adding up what would be the sum of terms over as about the cusps and these aspects of the topological features of the line, that by bracketing a sufficient area around it, you essentially measure a stripe centered on the line, and that this kind of approach is as for similarly when numerical methods are used to approximate and to a very high degree of accuracy approximate the length of a line, that these are methods that are kind of surprising because when we have something like Riemann sums or Lebesgue sums, where Lebesgue is basically only different than Riemann in that Lebesgue measures horizontal areas of vanishing height, whereas Riemann measures the vertical areas of vanishing width. Then there's Stieltjes, and then we get into the meromorphic and how you can have free analysis on the plane and this kind of stuff. When measuring the lines in the line integral, there are a couple different approaches, and make for why it's difficult to compute such things as the catenary curve, where the catenary is fundamentally defined as what is the shape that a hanging wire under tension or the cable will make as it naturally falls in a uniform downward well of gravity. And so it's built up these days that it's in terms of potential, and that you add up the potentials, and so by either minimizing or maximizing what would be the difference between that and a free falling or arbitrarily random motion, that you end up having the line integral, or various setups that result various approaches to measuring the line integral. So the path integral basically is as of when in the quantum dynamics that this particle, as we've been discussing, the particle, the quantum, as of the denormalized, of the renormalizable, the continuum analysis that's a quantum mechanics, it's continuum mechanics of the particle mechanics, that the quantum particle has the behavior as that it moves as of about its sum of histories. And so the sum of histories is not only including the linear motion of the line, and is according to, for example, the geodesy, which is according to Minkowski spacetime and a projection of it to having a curvature according to the gravity wells of things. It's always instantaneously evaluated and always results that is restitutive when objects come together. or as they meet, that there's the local after the point and the global for the total approaches in the Machian of what makes these potentials. That similarly and primarily, the path integral was invented as a way to compute what would be the distance traveled by quantum particles and as accords to the fields they are in and what they inhabit of this unified field theory that basically places for a field of gravity, if you have a theory of fall gravity where gravity is a central and the central kinetic thing, and then that there's charge, and the charge and the atom are the two major force carriers of unified field theory, where you have strong nuclear force and then electricity and the electrical force, and then there's the weak and electroweak, and there's gravity as what unifies that, as being that a fall gravity is the strong nuclear force with regards to gluons and quarks and the subatomic, and what that results in why string theory is really a thing for continuum mechanics underneath the Planckian regime, which is about 5 or so orders of magnitude smaller than the electron and small enough that its graininess is smooth. That the path integral, and then is to add up the sum of histories. And so the idea is that it's possible to approximate and build this path integral as over this courses, so that these nonlinear contributions that, as we've been discussing about Mauguin, that the potential theory of the day as applied is the theory of harmonic functions, and in the near field and far field, and how we've been talking about those with respect to our classical wave motion and these sorts of things. That then something like this book by Mark Swanson of path integrals and quantum processes is a collection of the day that's really quite new and recent. And I picked up a copy of this book for not too much money. It's from UConn at Stanford, Department of Physics, Stanford, Connecticut, Academic Press, Harcourt Brace Jovanovich. And it was published in 1992, this book. So when we first looked at this book, and then some of the talks after reading Mauguin and the nonlinear electrical mechanical effects and applications, the mathematical preliminaries, as we noted, were the same between them too. And so then in chapter 2 is titled Quantum Mechanical Path Integrals. So I haven't read this book, but what I'd like to do is scan its derivations here, and that chapter 2 is quantum mechanical path integrals, that the mechanics of the quantum after the mechanics of the continuum, and the Copenhagen interpretation, and that we're talking about particles as are fungible quantities in this theory of waves and harmonics and resonances. That then chapter 2 is quantum mechanical path integrals. Chapter 3 is evaluating the path integral, and here, as we talked about just recently, there's like purely analytic forms and closed forms, and then there's these numerical methods which are not closed forms, and they are always having the rest of the sequence or the error term, but they may be computed to arbitrarily high degrees of accuracy, and thus that they are widely applied. That the evaluating the path integral is difficult to achieve closed forms. And then the chapter 4 is into applications, and then chapter 5, as we talk about the Grassmannian, and that's in the realm of the hypercomplex up into the octonions, that we have Gaussian Grassmann integrals, where the Gaussian integral is usually as with regards to the complex field theory. And then he gets up into talking about field theory and scattering theory and its complement tunneling theory, which results for these models of particles that they represent the radiations of the impulse or the gradient of these fields. And then gauge field theory, where the gauge is defining the scale as of about the measure and metric and norm and the things. And then two various applications that involve frameworks and setups in the perturbative, which is as of the variational principles. When something is disturbed in a very slight manner, is to jiggle or joggle it, and so that results that it would leave what would be like a local minimum or local maximum in terms of that, otherwise that in the chords that a particle may sit in a local equilibrium that doesn't really affect the global equilibrium. So that's kind of something that gets into what are otherwise these variational principles and methods of perturbations and hypothesis of small perturbations, as Mogan put it, because it helps then when we have a continuous grain and the particles are, their lattice, that it makes for a framework to establish above that how to sum up then the gross and the aggregate of those as they come back around. So chapter 2 starts at page 31, and it's after he's defined the Dirac deltas we're talking about in functionals. So modeling a function as a limit of standard functions. For a while in physics it was called modeling a function as a limit of standard functions. And thus you can have non-standard real functions like the Dirac delta, the Heaviside step, and for example the natural unit equivalency function, which I still build. Then functionals are a similar thing, and also in distribution theory, where a distribution is from probability theory, it's a function and the area under it is 1. So it identifies a continuous random distribution. That's one of the fundamental things of probability theory, that the CDF, cumulative, and the probability distribution function and cumulative probability density function and cumulative distribution function and the moment generating functions result that the distribution is from the language of probability theory, whereas the functional here is kind of described in terms of a real valued function, a mapping from some space into the real numbers. It is a real valued function. That is the limit as here is as an epsilon, which is usually representative of an infinitesimal quantity, goes to 0 of the difference, kind of like when we established the fundamental theory of differential analysis when h goes to 0. So this is part of the preliminaries. Then he talks about the chain rule and in terms of delta the finite difference, d the differential, Greek d the partial differential, and some setups in matrices as when we have our transformations about the special, ordinary, orthogonal, and unitary matrices. These are things. Then that there's, as of getting to page 31 here, into the Gaussian integrals, it will be seen that the evaluation of many path integrals reduces to evaluating a product of Gaussian integrals. The Gaussian integral has already been encountered in exercise 1.5 and is given by the integral from negative infinity to infinity in dx of e to the negative alpha x squared equals root pi over alpha. Now, one point of note of this author is that oftentimes when you write the integral bar in Leibniz's notation, you'll have the integral bar on the left and the terms in d on the right, and in the middle will be the integrand. Here, this author writes the integral bar and the derivative right next to each other, and then has the function that's evaluated over as the indefinite integral for the definite integral written just after that. And I think that's a fine notation because algebraically it's no different, and there's some consideration that you can't really treat the terms as how you might say not one quantity in terms of later evaluating that as a quantity, that you need to keep in mind the terms underneath that went into it, especially in numerical methods, which would otherwise lose the guarantees of their precision and their asymptotic behavior and as about their error terms. That though, writing the integral this way seems a good thing, and I don't really see it very often just because everybody writes the integrand in the middle. But it probably is a better way once you get used to reading it. So the Gaussian integrals admit a particular thing about the integral of e, the exponential function, or here I mentioned that's just the natural logarithm constant, to the negative alpha x squared. That this particular quantity that falls out of it in a usual case is that not always guaranteed. the author goes on, however, the Gaussian integrals appearing in some forms of the path integral will have the corresponding alpha pure imaginary. And this goes back to the talk before a bit about how in our solutions of differential equations that we end up being only really interested in those that have meaning in the units that are real valued, and so that the imaginary, which is used as an adjunct in the projective space, ends up not being a sensible solution, or as it represents a sort of degenerate solution. And so when we're talking about here, as the author comments that the alpha would be imaginary, he continues that the problem is then to evaluate this form of the Gaussian integral. In order to do this, methods of complex analysis must be used. And this presents the opportunity to review briefly a few of the most important of these. So then he's just describing that when we say Gaussian, we basically mean in terms of using the algebra of the complex numbers, which have the scalar real part and the scalar of the imaginary part, and that the imaginary number I and complex numbers by themselves is the square root of -1, the principal square root, I guess you could say, though usually again that's the real value, and that the principal value is the positive and real value when it doesn't make sense in units that something has a negative value. That here he just goes on to describe some of the things that get involved in functions of a complex variable with applications, kind of like this manual that was kind of an honors text from England, and they have a bunch of these Oliver and Boyd books, which were basically represented the math books of the day, that we'll get into later. That he describes we have the Argand or the Wessel plane is another name for the complex plane, but we have different uses and applications in the framers of the Argand plane and the Wessel plane of complex numbers about polar analysis. A function of a complex variable may then be written ... The function f is said to be analytic at a point z if it satisfies the Cauchy-Riemann conditions that du dx equals dv dy and du dy equals negative dv dx. That this orthogonality of a sort ends up being that the Cauchy-Riemann condition thus makes it so that the function is able to have applied these methods as about computing its line integral. Kind of when we were talking about drawing the stripe along with the line and measuring that, dividing it by the width of that, or so on. That the idea is that the function is said to be analytic at a point when it so satisfies its property and criterion. If a function f is analytic at a point, then a unique value for the derivative df or dz exists at that point. And here is speaking that otherwise the derivative is a function, and that some functions can be one to many or many to one, and we're talking about having a unique value for that. Then in terms of the space of complex numbers and having roots there, then finding a unique value is as of finding a principal value, and as of otherwise figuring out after roots of unity and infinite primes at infinity, and these kinds of things about primes and roots and factors and powers, that he's establishing in the preliminaries what a Gaussian integral has as properties that make it amenable to getting out numbers crunched from some systems of interest and conditions under which that is so. A function of complex variables may be integrated along a path or contour in the complex plane. Now, is there a difference between a path and a contour? A path is as of in a surface or on a manifold, and the contour is as of about and around it, kind of like the notion of the great circle. He goes on, where the line element along the path is given by dz equals dx plus I dy. The line element is basically that any curve, when it's curved, at any given point has a given direction in that point, even though it's curved. So basically that's at the tangent to that point. The line element is as that unit line element pointing in that direction tangent to the curve is on that path, it goes to 0. It's differential. Here the raw differential, or writing dx by itself as an algebraic quantity, is again guided by the principles that it can't be treated as a distinct independent quantity, except that it's in these systems of equations and quantities. Of particular interest are closed contours. Cauchy's theorem states that if the function fz is analytic everywhere in the part of the complex plane inside the closed right-handed contour C, then the surface integral of C, which is the integral bar with a little circle on it, or the contour integral of C dz of f of z over z minus z naught being the initial value, equals 2 pi I f z naught. That it's reflecting that there's this period of revolution, is 2 pi, and that it's about this polar analysis as about the complex analysis, that it works out that in this framework, in this setting of the Gaussian, the complex functions in their theory, that it's a thing. If z naught is a point inside the contour. If z naught lies outside the contour, then the integral vanishes. Goursat's, G-O-U-R-S-A-T, Goursat's theorem states that if fz is analytic on and in the region bounded by C, then counter integral dz fz equals 0. And so this establishes an identity, as we've been talking about. The additive identity is 0, and the multiplicative annihilator is 0. That having it so established like so makes it, for that, the integral of that, the area, is as of about that region, that it's closed in this manner. Then he has an exercise. Using Cauchy's theorem, show that if fz is analytic in the part of the complex plane enclosed by the contour C and the point z naught lies inside the contour, then the contour integral dz of fz over z minus z naught to quantity to the n plus 1 equals 2 pi I 1 over n bang dn fc over dzn, given that z equals z naught. So here we might read that into, by substitution of terms, and that the term z minus z naught is simply multiplied, or by itself taken to the power of n plus 1, that it falls out of that when the 2 pi I of z naught is like so, that 1 over the factorial of n is carried down as a multiplier. This gets into the, I would imagine, the scalar product of, or dot product of vectors. When you take the dot product of vectors, and it multiplies the length by the length of those vectors, or is that scalar product, that it's a way to see that that scales out as over the different powers of the rotations as around this z minus z naught. Then it's maybe a way to look at an approach to defining, besides maybe some other readily available results from complex function theory, that taking this out of complex function theory, put it into a vector space, applying this result, and just noting that the internals of the complex function theory would arrive at these quantities dropping out, that would make it so that maybe that would be a solution for this. But I have not completed that yet. A function z may be expanded in the neighborhood of a point in the Laurent series. Here he describes a series that results. Fz equals n equals negative to infinity, the sum of all those integers from negative infinity to infinity of a sub n of z minus z naught to the n. The results listed so far can be used to prove the residue theorem. So residues are a key thing, and I need to refresh my understanding of them, and here they're about the field of complex analysis, and why the complex analysis is just taking advantage and exploiting the fact that the complex algebra has these closed forms as about the polar and about the rotational in uniform periodic motion, or going around things and forming complete circuits in their paths of these things. That the residues are something to get figured out then with regards to generators and residues. ... where the Laurent series converges, i.e. that it needs to be established what regions it doesn't have these things. And then he goes on to describe analytic continuation. This is accomplished by extending the function exponent of negative IAX squared, where alpha is both real and positive, to a function that is analytic everywhere in the complex plane, but one that reduces to the original function on the real line. So this is, as we talked about, the abscissa and the ordinates, and the notion of that a given curve is projected out into a box, so that then you can frame it as in the box. Besides, otherwise the coordinates are just kind of its extent. That you actually put it in a box, and then that you, by drawing it out to these coordinates that follow, you make a shape that here is called the analytic continuation, and will frame in terms of Mogan and the ordinate. the author goes on, such a function is given by exponent of negative alpha z squared. The Cauchy-Riemann conditions demonstrate that the function exponent negative alpha z squared is analytic everywhere in the complex plane and reduces to the original function when z equals x. If alpha is positive, then this function will be integrated along the contour depicted in figure 1.1. The path 1 lies along the real axis and extends to infinity, while path 3 lies along the line described by y equals x. Path 2 contributes nothing to the contour integral since it is damped by the factor exponent of negative 2 alpha x absolute value y, where x goes to infinity. Since fz is analytic everywhere, Gorsat's theorem states that its integral around the closed contour must vanish, the identity we spoke of, and this relates the integrals along the paths 1 and 3. It follows that there's that the integral from 0 to infinity of dx of e to the I alpha x squared equals 1/2 root pi over I alpha. So far we've seen introduced this term the square root of quantity pi over alpha, and this 1/2 square root of pi over I alpha. Extending the integration of the whole real axis gives the final result that the integral from negative infinity to infinity of dx times e to the negative I alpha x squared equals root of pi over I alpha. This is the same result as if alpha had been analytically continued to I alpha in 1.87. If I alpha is negative, then the contour must lie in the upper quadrant. However, the result of the integration is identical. So then he discusses a generalization of the single integration to n real variables, so that then when we get into our vector valued variables and tensor valued variables, that an analog exists. And as about the establishing that's Hermitian, so that its adjoint is so, then choosing a particular matrix so that A prime equals U transpose AU is a diagonal matrix, then that he sets up an eigenvalue problem in the eigenvectors and sets it up as a Jacobian, as much similarly how we talked about in Mogen. And about the unitary transformations, as we get up into the special unitary groups, which are a source of many great symmetries, especially as with regard to when you have multiple fields and you can establish that they have particular analytic or orthogonal inputs, thus that they don't interact or become dominated by the nonlinear terms, that they're essentially fundamentally a collection of linear terms together. That in this manner is one way to think about how it's possible that all these towers of formulas make it so that it's simple to draw a line and easy then to compute its length, which it is not. It is quite a stack. And it employs the methods of matrix theory, the methods of the eigenvalue setup, methods of determinantal theory, methods of complex theory, the methods of Gauss's complex theory. When we get to talking about Argand and Wessel, then we have the analytic methods is about the analytic continuation in the whole field of the contour integral, and that particular setup. This section is about the Gaussian integrals, helps bring together a lot of different things that before in the preliminaries as about the matrices were as of about the Hermitian and the various ways that matrices are set up so that given products of them by what's in the middle is so defined, and that then we have Jacobians and the Hamiltonians and HJE, that the Hamiltonian Jacobian equations, which are used in this harmonics and function theory quite extensively in the literature, and you can read this on the wiki. And then after the definition of functionals and what are non-standard functions that have been employed to make these things for what is, as is concludes, that this technique is referred to as a saddle point evaluation and will be used throughout what follows. All right. So he provides and references Arfken, mathematical methods for physicists, Courant and Hilbert, methods of mathematical physicists. Courant, most famous for the soap bubbles and what natural systems have automatic, like the catenary, the minimizations of potential. PAM Dirac and his delta, quantum mechanics. A mathematically rigorous definition of the Dirac delta and a presentation of the general theory of distributions and test function spaces can be found in I. Halperin, Introduction to the Theory of Distributions, University of Toronto Press, Toronto, 1952. Well, that's nice to know. I was not familiar with it. Halperin I've heard of, but now I need to go see what he says about non-standard functions and the conditions where their analytical properties are guaranteed. Concepts of functionals stems from the work of Volterra, Volterra, Opera Mathematische, Accademia Nazionale dei Lincei, 1954. A standard mathematical treatise on Fourier series and integrals, as well as completeness, is E.C. Titchmarsh. Introduction to the Theory of Fourier Integrals, Oxford University Press. Hilbert's space theory is discussed in any standard text on functional analysis. See the excellent treatise by M. Reed and B. Simon, Methods of Modern Mathematical Physics. Well, all right. Development of a rigorous calculation of the variations is described in an M. Klein, Mathematical Thought from Ancient and Modern Times. So this is a variational principle and hypothesis of small perturbations and these things. Definition of functional differentiation used in this book has its originations in the functional methods for quantum field theory pioneered by Schwinger and Szymanczyk. Functional differentiation techniques of H. Fried, functionals and functional differentials in Schulman. The formulation of classical mechanics in terms of a variational principle began with Lagrange and Hamilton, and Hooke's law is relevant. For a detailed introduction, see H. Gruib, linear algebra. Linear algebra has lots of applications because it's a rectangular array of numbers, and any possible way you could define arithmetic in algebra, those is what it works out to be. I have a hard time with matrix arithmetic. It's not very compatible with what I recognize as symbolic variables, but the idea is to get it up into symbolic variables and then to be ignorant of what's in the matrices, because their random arrangement doesn't really mean necessarily much in terms of their scalar values or what results. That linear analysis makes heavy use of those. The proof of the Baker-Campbell-Hausdorff theorem presented here can be found in J.D. Bjorken and S.D. Drell, Relativistic Quantum Fields. And then he says, for a detailed introduction to complex analysis, see, for example, R.V. Churchill, Complex Variables and Applications, McGraw-Hill, 1960. All right, so his preliminaries and his methods and such are kind of established as from the same milieu as this thing. And so thus begins Chapter 2, Quantum Mechanical Path Integrals. Now I'm just going to kind of scan this. I'm looking for what sticks out as what makes this any different than usual linear thinking, that makes it so what defines it as its properties is how it has a complement, that what resolves, when it's resolved, how this difference exists, that it becomes a unified thing, that it is so. The path integral will be derived as a limiting expression from the fundamental structure of non-relativistic quantum mechanics. Well, that just reminds one of Leonard Weichart and the test particle and quantum mechanics. When he says non-relativistic, and that gets into the conditions where something is analytic and this. In this sense, the path integral is a representation of quantum mechanical amplitudes, equivalent to the usual wave mechanical or matrix formulations of these same amplitudes. Yeah. This kind of path integral is not necessarily the sum of history's path integral. Kind of like potential theory, when they say, well, potential theory is our theory of harmonic functions. It doesn't say the theory of an infinite sequence of harmonic functions. When we talk about vector spaces, we talk about a theory of vector spaces and finite dimensional vector spaces. It doesn't include a theory of infinite dimensional vector spaces. So the path integral is the sum of histories, is the sum of all the potentials, and as evaluated over those instantaneously, each and all over the whole thing. That here he's in this setting, Swanson's, whereas he's certainly free and fair to define it for this work. Path integral is it's the quantum mechanical, so it's quantized and it's denormalized. B, it's the probabilistic amplitudes, so it reflects quantum numbers and their amplitudes, and that those are as of for quantum theory, for continuum theory, for probability theory, that there are Fermi bows and there are and Einstein and Dirac, the statistics, which later in the quantum mechanics get into what's called parastatistics, as what result that those measurements that are possible to make in the sampling, observation, and measurement have, and the mathematical models that are just a finite box, and that the numbers are truncated and cut off and fit in a finite range, and that they're quantized also in terms of orbitals and energy discreteness, wave packets, that this is just establishing a setting where it is so that this is how these things will be computed, and under given things it will be pretty close or precise to 29 degrees of precision, 29 orders of magnitude, which is where quantum mechanics and relativity are both at these days. This is extremely useful since there's no ambiguity in the path integral's definition. That is to say, this is applied. These are the requirements of the inputs and outputs of these functions for this behavior to be defined, and it is extremely desirable and to have this incomplete yet consistent setting that carries all these things like so. And so that's fine. Well, at the same time, the real path integral is the entire sum of histories, and has to deal with both the complements of scattering theory and diffusion and tunneling theory. For this reason, the form of the path integral derived in this case serves as a motivating form for a generalization of the path integral to all quantum processes. He's introducing that, at least in its initial terms and its lower order terms, that this does form some approximation. It doesn't say anything about that the following terms would either go to zero, which they do in these happy cases, or that the nonlinear, as we've been talking about, them higher order terms eventually dominate the initial linear terms, and as to where a generalization of the path integral to all quantum processes has that it's as of a method, not necessarily as a closed form, which is fine. So he says in section 2.1, the relevant aspects of basic quantum mechanics are reviewed. Section 2.2 is used to find the path integral form for a quantum mechanical amplitude. Section 2.3, the idea of the path integral as a sum over histories is presented as a conceptual generalization of the results of section 2.2. So he does introduce the context that is sum over histories is our context, or sum of histories. Some of the formidable and mathematical difficulties associated with this generalization are sketched. Then briefly, he mentioned the Hamiltonian and classics. We have Bra and Ket. The left angle bracket is named Bra, and the right angle bracket is named Ket. And in between them is what we have C, bracket, a bracket, that the elements of the Hilbert space. We talked about the eigenvalues of the respective operators. The Hilbert space is equipped with an inner product. The inner product is known bracket, psi, C, phi, and obeys that psi, C, phi equals, phi, C, psi equals psi, C, phi star. That this reflection principle establishes that, so that its form is analogous to the inner product for the functions. The inner products of ket B and ket Q, so that these states are orthonormal in the continuum sense. In the continuum normalization, recall that renormalization only had to follow denormalization. That the normalization is as of often, for example, for an amplitude as establishing about the central limit theorem, that's a standardized normalized central distribution, or that otherwise units are made natural, meaning, well, it's infinity or max, and we're going to call it 1, and keep everything between 0 and 1. And then coupling an algebra with the inner product gives a coordinate representation of the momentum operator. The operator spaces, operator theory, operator calculus, operator spaces, here's dimensions. That's when things get the most tractable, if the least fungible, because it's way, way, way above the detail. It's up after the algebras and the products, and all these transformation rules are so applied that then you can talk about the operator theory, which is really general in lots of different levels. But that operator theory is basically superclassical. This in turn gives the inner product. The factors present are necessary in order that a particular relation holds. Indicates that the classical mechanical Poisson brackets of two observables, brackets of two observables must be replaced in quantum mechanics by commutators, establishing the commutator property in the manner that then we get talking about 1 over I h bar, which is Planck's constant, which is small and normalized as in some natural units, but really is reflects the Planck regime where things get nonlinear, and total physical system, standard differential version of Schrodinger wave, Now, excuse me, any errors are my own, and I'm by no means reading all this out. Looking for the particulars. He has Heisenberg brought up, so he has time independence of transitions. And this is a conceit to that otherwise the gimbal lock or similar kinds of phenomena that make for that a local minimum or maximum would lock the mode, where the mode is what something is and where it would stay. That there is that here. The transition amplitude then gives the probability of the system transiting between the respective states as p equals absolute value of z squared, or as so under this norm, so that z describes a quantum process. And so a quantum process here, we often call that parallel transport, instanton. A parallel transport is the usual idea how any kinetic body or anything that's a particle carries. And the sum of histories, it's along with other elements in this field, and so it represents a wavefront of a Bohm de Broglie style Brill wave, quantum. In the next section, the transition amplitude is given as a path integral representation. So then section 2.2, the path integral derived. He introduces picture states, the instantaneous eigenstates of the Heisenberg picture operators. So these are kind of like the line elements that we talked about in the contour integral. For operators, that they're instantaneous evaluations that need to be summed over the sum of histories. So then we're talking about the path integral. The transition element is sometimes referred to as the propagator, since it contains all the information regarding the time development of the system. The time interval, TB minus TA, is first partitioned into n infinitesimal steps of duration epsilon equals TB minus TA over n, where the limit as n goes to infinity is understood in everything that follows. So this is a lot like the equivalency function or what. It's the same. And what it means is that it's to reflect that the precision is according to how big that effective infinity is, where n is capital N, and it's for the infinitude of the natural numbers, as is often written, blackboard n, that then this epsilon is iota. I call iota values, these infinitesimals between 0 and 1, they're iota values, and they have different arithmetics for addition and multiplication, and that the n is the usual name for omega or infinity, where the limit n goes to infinity is understood in everything that follows. Then n minus 1 complete sets of intermediate instantaneous Q-ket eigenstates are inserted into the transition element sequentially at each of the respective times. So it forms what's called Dirichlet or pigeonhole principle, that between all these boundaries and partitions, you have one between them also. So the Dirichlet or pigeonhole principle is a usual mathematical thing that you use to establish that as if you had a bunch of cubbies of pigeons and that they all have one, that then you can't insert one more, or you have to take one out to put one in. Dirichlet is what that's called. This gives then that Z, the propagator, as what we were just talking about, the amplitude of one of these tiny regions is the integral of all the different multivariable things. We were talking about the Gaussian and bracket of the middle of this little interval all the way to the end. So he's just written symbolically that, well, here, let me write the formula for this. It's add up all these infinitely many things. So that's what it is. So that the whole transition element has been reduced to the product of n transition elements, which are infinitesimal in the sense that their time difference approaches 0. And all these other conditions hold. Since the time difference is epsilon between the two states, it follows that the bracket is the bracket of e into the negative I epsilon HPQ over H bar, Planck's constant, with C, or what's in the middle of the bracket, this guy, this term in the exponent. In order to proceed further, it is necessary to select a convention that will be used consistently to reduce all the infinitesimal elements. To evaluate the matrix element of the exponentiated Hamiltonian, the exponential must be expanded in a power series. After the expansion, all the p operators will be moved to the left and all the q operators will be moved to the right. For want of a better name, this will be referred to as coordinate ordering. The final result of coordinate ordering as a product of p's and q's will be that all the p operators lie on the left side of the expression and all the q operators will lie on the right side of the expression. The coordinate ordering operation will be noted by C in operator theory and operator calculus and operator applications, so that, for example, C of p cubed p squared equals p cubed q. Obviously, the opposite convention can be selected, and it is natural to consider the possibility that the existence of different ordering schemas might induce some ambiguity in the resulting path integral. Oh, well, so he's introduced a convention, and then we'd associate with all kinds of right-hand rule conventions, right-hand contour conventions, and all the ways which results in basically when you label X, Y, and Z, and then you kind of roll your hand and make a fist and make thumbs up, that it results that that's the direction it points up. Now I'm reading a bit more of this. Because of its use of the Baker-Campbell-Hausdorff theorem, so that the effects of the commutator are irrelevant in the epsilon goes to zero limit when it's an iota value, as of about the Planck regime. This verifies the intuitive notion that for infinitesimal time periods, the time development of the system is overwhelmingly dominated by classical dynamics. Yeah, he's established that in this case that this quantum process is like so, and there are others, and he makes that clear that at the same time it's like so. So it doesn't really stick out much that he except the idea of the infinitesimal transition elements is where all the magic are real things that happen about the otherwise nonlinear effects that are the rest of the path integral occur. That this just speaks again to the importance for non-standard analysis of real mathematical infinities and infinitesimals for physics. Mathematics owes physics a bunch of mathematics about how that works. So this deserves much further reading, and I'll get to it a little bit later. And I very much enjoy it, and I think it's quite a good introduction to path integrals and quantum processes, in particular the linear development, and then what we would be able to take away as of the conventions that are used, the conventions in the symbols, the conventions in the notation, the conventions in the systems, the conventions in the setups. These conventions that result that then we can have shared and common results, so that all these preliminaries and definitions that are carried forth in this book, and which goes on to fill a complete and interesting collection of applications, is about these, and for computing the path integral, and for scattering and tunneling what happens in particles as they are waves, and they move in the quantum background of the Dirac positronic sea of a vacuum or any media that they encounter in terms of surfaces and the continuous manifolds thereof. It's a pretty good reference work, and it was well worth the $50 or whatever I spent to get this copy. So then the other thing, today I went to the bookstore, and the bookseller is pretty familiar with my, interests, and that I'm interested in books that have to do with physics. And so what he had set aside for me was this something from Richard Feynman. Now Feynman was this guy who was is very famous. After Einstein, Richard Feynman was probably the most revered and famous physicist that most people know. Then at one point in time, it became kind of Stephen Hawking. If you were to ask somebody in the 1980s who is the most well-known famous physicist of the day who wasn't Einstein, they'd say Stephen Hawking. But if you ask anybody before that, they would say Richard Feynman. And so what he was most famous for is quantum mechanics. Kind of like Einstein is most famous for relativity, but then he had to deal with all what's going on in quantum mechanics, and he was working on a total field theory ever since he invented relativity. Feynman is kind of similar, and that he did a lot of work in the quantum mechanics, and he's out of Cleveland, Ohio, or Columbus, Ohio, or something like that. He's like, if we were the Hoffmans or whatever, then they were the Feynmans, and that's a story about how at one point Ohio was kind of the west of the United States. There's Case Western Reserve, Michelson Morley, and all that kind of stuff in the industry, or out of Case and that kind of stuff. Then that later, Feynman was involved with like the H-bomb, hydrogen bomb, in its development, because it involves quantum computations and quantum processes at a very low level in terms of the radionuclear and these kinds of things that have to do with what we call the electroweak effect, which is very involved with the strong nuclear effects of the unified field theory that we mentioned. So anyways, I walked in there today, and the guy's like, hey, I found something you might like. And it's a 3-volume set of all these lectures of Feynman. So the lectures of Feynman, this you can get this anywhere, of course. You can probably find it online. And what he's got is just space-time intervals, disintegrating particles. So he's already talking about working up his diagrams and what happens in the transitions of things, and all in terms of trigonometry and geometry, where trigonometry and sine and cosine are orthonormal functions, so together they make all kinds of identities, and they can be used in all kinds of transforms. The energy of an oscillator, as we've been discussing about the restitutive and the oscillating, and the dissipative and the attenuative, and what would they mean with regards to the essential tendencies and propensities of the milieu of scattering theory and tunneling theory. That this is a discussion of transience when we talk about the permanence and transience. And then linear systems, how we need to keep things in the linear as much as possible because it's the only tools we have in many cases. And he's got some interesting stories. This is basically a transcription of his lectures. He's very famous for giving entertaining lectures and having quite a strong recollection of what came from his interest as a young man in the electrical. And he says it took 30 or 40 years before the next difficulty was discovered, and that had to do again with statistical mechanics, but this time the mechanics of a photon gas. That problem was solved by Planck in the early years of the previous century, or that fin de siècle we've been talking about. Equipartition of energy. Now, equipartition is a thing, and it's kind of like we were just talking about the Dirichlet and the equipartition of the infinitesimals in the unit. That equipartition is a thing, especially when it becomes very smooth, the grain. That he talks about Clausius-Clapeyron equation. That's about the change of vapors to other phases, or what happens in the aggregate and the bulk when the conditions aren't anymore as of the test particles and the discrete ones, but become aggregates. And this reflects on what we've been talking about, the molecular and of course the waves and resonances and these sorts of things, about what happens when there are the dynamics of the continuous and discrete. And Feynman was very famous for enjoying the bongo drum, and sketching dancers was his thing. The waves and solids. So that anyway, I've acquired this Feynman lectures and it's large print, and what I'll be looking at is to find when he starts talking about his intuitive and formal things that go into something like when you read QED, which is Feynman's book about quantum electrodynamics, and it's interesting if you're into that. And it's also amusing that QED also, besides for quantum electrodynamics, is quod erat demonstrandum, or I proved that, that QED is a thing, that it's a complement, of course, to quantum dynamics, and then which is usually just called quantum mechanics, and that there's statics and mechanics and statics and dynamics and mechanics. That there's a quantum chromodynamics is about the color force, and it's usually written the British way with COLOUR, color force, which is involved in the strong nuclear force, and basically reflects the asymptotic freedom of the quarks and gluons as their a representation of the state of things kinetic, or the atom, which in a fall of gravity is a real graviton. That it will so follow that these Feynman lectures provide a bunch of different things, and he talks about the nuclear force field. We would like to make some further remarks about the part of the mass of nuclear particles that is not electromagnetic. Where does this other large fraction come from? There are other forces besides electrodynamics, like nuclear forces, that have their own field theories, although no one knows whether the current theories are right. These theories also predict a field energy, which gives the nuclear particles a mass term analogous to electromagnetic mass. We could call it the pi Masic field mass. All right. It's presumably very large, and because the forces are great, and is a possible origin of the mass of heavy particles. But the meson field theories are still in a most rudimentary state. And this gets into when we talk about some of the, and a lot of the quantum properties that could only be really set up in terms of the electron experiments, and so that the energy involved in the electron in its propagation was interpreted as about the mass of the proton, the electron, and the proton, its corresponding particle in terms of the charge carriers, the force carriers, in terms of one theory that's kinetics and the other theory that's charge, and you try to write them both the same way, and they both result in energy. Then when we talk about massy and massless particles, that basically the only massless particle is a photon that carries energy, and that the other ones, in terms of the weight of those particles, are also about the energy. That there's a confounding of the definition in these quantum systems of things like rotation and angular rotation as about quantities of the quantum numbers in the field occupation formalism, which is what numbers of these quantities go in the space-time manifold, each point in space, its contents. That there's a lot to get figured out then with regards to like these amplitudes and quantum probabilities, and after Dirac and after Copenhagen, and then for Bohm and de Broglie and real wave functions, that these represent superclassical waves of a sort that kind of snap at the back and instantaneously, infinitely make a ghost wave that builds at the front, as opposed to, you know, ringing the bell with a little hammer. That these are the kinds of things that go into why then it involves various descriptive frameworks and various mathematical frameworks, and it's going to work out a theory that unifies the frameworks in simple terms, respectively, relatively simple terms, that make it possible to approach this, instead of like these days having to get into 11 dimensions for superstring theory. Well, first we draw a line and make one field theory, and then all these different dynamics can be built up in higher order projections. Because as it is, instead, there's a conflicting confounding of the units and quantities, and so it involves all this mathematical machinery that has an explanation that's much simpler in terms. That's the way it's going to be, because that's the way it is. Well, all right then, I hope this finds you well, you and yours. I hope this has been entertaining, and that if you already knew all this, I'd be very interested, because you would be a world-class particle physicist. Well, all right, friends, have a great day.